Okay, so as I was saying, just using the chi-square bound, the bound for chi-square, for the tails of chi-square distributions that we saw earlier in the class, we have that that the probability, right? This is just a chi-square distribution, right? Where we just sum S standard Gaussian squared. And we know the probability, its expectation, right, is of course S, because the square of a standard Gaussian is expectation 1. And the tails are given, there's a bound on the tails given by this, right? So now, if we, if we want to do it, if we did this for a fixed support, but we want to do it over all supports, right? So we can just union bound, right? We've used this technique a few times, right? We just use the union bound, right? And so we just have to union bound over all possible sets, right? And so then we know then that the probability, right, that now we take over the max or any of the sets, right? But any one of the sets being bigger than this, it's the same as the max being bigger, right? So the maximum over these sets, set of n, whose size is S of G squared. This is being bigger or equal than S plus 2 square root S square root T plus 2T, right? This is smaller or equal than, right? The union bound says that the probability of the union is smaller or equal than the sum of the probabilities. So here the probabilities are all the same. So we just have to count how many supports we have, right? But this is just n choose S exponential of minus T. Okay, so now let's scale this a little better, right? Just so that S shows up everywhere. Let's scale this as T being, I guess, SU. And then what we have that the probability, right? The probability that, this max of G tau squared being bigger or equal then, right? So now I guess an SU, I get an S root U here. So let me just put S1 plus 2 root U plus 2U, right? So that this way I have now on the scale, smaller or equal than n choose S exponential of, right, minus SU. Okay, so now we just have to estimate this, right? And this is also a standard thing. Right, so we know, okay, so let me maybe do a couple more steps. Okay, so the probability that this is smaller or equal than the, okay, so maybe let's do probability of max now inside n, size of tau being S, tau being bigger or equal than squared, bigger or equal than S1 plus 2 root U, 2U, smaller or equal than n choose S exponential of minus SU. Okay, now a standard thing is to move the n choose S inside the exponential, right? Because what is this? This is the exponential of minus SU plus log of n choose S. Now it's a standard trick that log of the binomial coefficient, right? You can see this fight like Stirling, is essentially S log n over S. I mean, if you want it exactly to be smaller or equal, then really you need to put an E here. But this E is like nothing, right? E as in like the, as in the base of the exponential, right? And so this is smaller or equal than exponential of, right, minus S. This will get an S log n over E, so I can put the S here, U, and then because I took the minus, I need to put minus here, right? The S went over there, log of n E over S. So this means, right, that this starts being really, really, really small, this probability, basically when this term starts beating this one. right? Because then the thing here becomes positive, the thing inside the exponential becomes negative, and so the probability starts being very, very small. And so this starts happening roughly when u is like a constant, right, up to constants, is bigger than log ne over s. But since we're talking up to constants, then the e is just like a +1, so it doesn't even matter. So just n over s. Right, and so once u is bigger than say 3 times this or something, then the probability starts being really, really small. So it means that we really expect. Okay, let me maybe erase here. Right, that the typical value of this max, right, the typical value of this will be s times 2 square root of u plus u, but the biggest term, right, because it's a log, the u term was bigger, plus times, right, times the 1 is so small comparatively, right, up to constants, we expect this to be like s log n over s. Right, the probability that this is much bigger, say bigger than something, a very large constant times this, is very, very small. Now, to get a control on the expectation, we just need to integrate the tail. Right, as long as we could just integrate the tail, because the tail is so small, and we would basically get, right, here I'm doing things without worrying too much about constants, but we get that the Gaussian width of the sparse vectors is bigger or equal up to constants of s log n over s. Right, and now what this suggests is that really the number of samples that I need, or number of measurements I need, is actually, this is the square, right? And the Gaussian width is just just the expected value of the absolute of the norm, not the norm squared. So this is actually the norm squared. Okay. So what this means is that the number of measurements I should require to measure sparse vectors should actually only be on the order of s times log n over s. Right. What's really interesting here is that even if I knew the support, I would still need S measurements, right? Because I still need to measure the numbers on the support, right? And this says with up to logarithmic factors, essentially, I can do that with just linear random measurements, right? And this is really at the heart of compressed sensing. I mean, of course, in compressed sensing, we also need to argue that we can actually then recover, that we can actually sort of unproject, right? And so we'll spend a lot of time doing that in the next lectures. But for now, it already gives us sort of the number of measurements that we expect to need. And indeed, what we'll see is that these are the numbers that of measurements that we will need. Okay? And in fact, we'll prove that using also Gordon on a slightly different set. Okay. So now we're going to do another set. We're going to look at the set of low-rank matrices. Okay, so depending how much time we have, we might cover a little bit of matrix completion, but if not, you'll get here just at least a preview of what it looks like. So here we'll be interested in the set of, we'll compute the Gaussian width of the set of low rank matrices, right? So take X, say a matrix that's just, it doesn't need to be square. So let's say N1 by N2 matrix, where the rank of X is smaller or equal than R, right? And of course we normalize them, right? Because in this cell2 norm, right? Which here, of course, the natural thing is the Frobenius norm, the sum of squares of the entries. And we're going to compute the Gaussian width of this set. Okay, so the set of matrices X such that this holds, right? And it'll be interesting in the Gaussian width of this. Okay, why? Again, this comes from one interesting motivation for this is matrix completion, is recommendation systems. Let's say that I have a matrix, right? And this was popular during the so-called Netflix prize, in which Netflix made a challenge to try to come up with algorithms to do this, right? But the idea is, let's say that you have some kind of online service like Netflix, for example, and you wanna really understand the following matrix, where maybe here you have users and here you have movies. And this is a matrix where in the entry corresponding to a movie and the user, you put the rating that the user gave or will give of the movie of course, after they watch it. Right. So this is a matrix you're interested in because, you know, if you can know this matrix before the users even watch the movies, then this is a very good way of recommending movies. Or if you have an online shop or some kind of service, if you have a good way of guessing the ratings that people will give to things before they actually even experience them, then you can make very good recommendations, right? And so now, of course, I'm sure you've been online places where you've gotten seemingly very accurate recommendations of things. And one of the basic algorithms behind this is something of this type, right? So you want to know this matrix, right? This will be our matrix X. So the idea, the modeling assumption that tends to be actually quite accurate is that these matrices are low rank. They tend to be very low rank, right? Why? I don't remember what the number was, but the engineers from Netflix, the time of the Netflix price, said that the rank was maybe like 7 or 10 or 15 or something like this, or at least, you know, very well approximated by a low rank matrix like that. Why is it low rank? Because maybe there aren't that many different types of movies, right? Maybe there's like, I don't know, 7 different types of movies, and then everything else is sort of a linear combination of those types of movies. Or maybe there are not that many different types of users, right? Maybe there's like 10 different types of users. Maybe they really like thrillers, or they really like, you know, comedies or whatnot. And every user is sort of a linear combination of them, right? So that's the modeling assumption. And then the question is, what if some users see some movies, or some people rate some kind of service? Can you fill up the rest, right? So how many and you can ask the question, how many measurements do we need? How many measurements before recovering the matrix? Measurements in order to recover the matrix. Okay, so if your measurements are just entries, right? You see actual ratings, those are the measurements that make sense. Then this is the problem of so-called matrix completion, right? So this is not what I'm going to talk about today. I'm going to talk about a slightly different problem, right? Which turns out they will be somewhat related, which is of matrix sensing. So instead of getting one, one measurement of an entry, we're going to get a linear combination of them, right? So this is what's called matrix sensing. Okay, but it turns out once you understand matrix sensing well, you can also understand matrix completion. But the nice thing is matrix sensing, we can relate immediately to the Gaussian width of something, and so we can do a calculation. Right, in matrix sensing, you just take Gaussian linear combinations, right? You take some matrix AI, and you take measurements of this type, right? This is just a linear operation of matrices, and these are your measurements, right? So linear Gaussian measurements, right? They're of course not the kind of measurements that you would get on a recommendation system, but there are applications where this comes up. Although, like, it would take me a long time to describe some, so let me, there's a mismatch between the motivation and the problem I'm describing for sure. But turns out that this is still related for 2 reasons. One, or interesting for 2 reasons. One, there are instances that are more of this style. And 2, once you understand this problem, right, this is just a problem where the AIs are very specific. And as we see also in compressed sensing, we're going to understand sparse recovery when things are a bit more specific as well. Okay, so we're interested in understanding the Gaussian width of this set, right? Because then the Gaussian width square will tell us how many measurements we need. And it turns out that it will be quite accurate even in this case. Okay, so let's compute this Gaussian width. Okay. Okay, so this actually is quite a simple calculation. Okay, so what is this Gaussian width? This is the max, right, over X being in expected value, of course. Okay, let me erase and do it properly. Right, the expected value max of N1 by N2 matrices. Right, we know it's Frobenius norm is 1, and the rank of X is smaller or equal than R. Did I use R? Yeah. Okay, and this is just the max of the trace of Gaussian matrix, right? This is a matrix with Gaussian entries. This is our little G vector, right? Here, this is like G transpose X, but in matrix language. Okay, So now in order to compute this, we just do, we just take the SVD of X, sigma V transpose. Okay, and now it's not hard to see that, well, of course, this we can just replace X by the SVD, but then we can send the V to the other side and the U to this one, right? So this, I'll try to do this without using as much. So this is the maximum over, okay, I won't worry about the dimensions anymore, right? Okay, so U will be orthogonal, like the part of the SVD. So U transpose U is identity, V transpose V is identity, sigma is diagonal, and the rank of sigma is smaller or equal than R, right? And the Frobenius norm of sigma is 1, right? The sum of the squares of the singular values are 1, right? And this is diagonal. Okay, and we can we can even take it to be just an R by R diagonal, right? This depends how we represent this. Okay, and so we have, right, we would have X, U, V transpose sigma, sorry, sigma, G, right? We send the V to the other side. So let me instead write V transpose G, U. So this just rotates these, right? It just rotates the image and, right, the image of G and the image of G transpose, sigma. Okay, but now sigma only has, sigma only has non-negative singular values, right? I mean, it's a diagonal matrix with only non-negative entries on the diagonal. So in particular, it's positive semi-definite. So it's not hard to see that this is smaller or equal. Again, I'm going to do the same max, right? Of, the biggest thing that can happen is sort of the leading eigenvalue of this lining up with, right? So if this matrix had all its eigenvalues equal to the biggest one, right? It was like an identity bigger times its biggest eigenvalue, then basically would have something like the trace of this times the biggest one here, right? And this is the biggest thing that can happen, right? It's not hard to see. It's worth thinking about it, right? So you can bound it. I mean, you can just prove that this is true given the properties of sigma. It's the trace of sigma. Okay, now what this means is that, all the max stuff can go in here, and this no longer shows up in the expectation, right? And so we have expectation of the spectral norm of G times the maximum over all those options of the trace of this, right? But what's the biggest this trace can be? Okay, let's think about this. So we have these singular values. We know that there's only R of them that are non-zero, right? And there's sum of the squares is 1, right? And so, of course, the biggest one, you can see this, for example, with Cauchy-Schwarz, the biggest this can be is square root of R, right? Because if you have R numbers, the sum of the squares is 1. By Cauchy-Schwarz, you see that the sum of them cannot be bigger than square root R, right? And now you have to understand what is the expected value of the norm of G, right, of the spectral norm of G, of the largest eigenvalue of G. This is like square root of the largest eigenvalue of say the Wishart matrix. That's the Gram matrix of G. That's one way of seeing it, but one can we know that this is roughly up to constant square root of n1 plus square root of n2. Okay, I mean, if when we saw this on the Wishart matrices, right, we were seeing the square of this, and it was normalized differently when it was something like 1 plus, right, it was the square, it was something like 1 plus the quotient of them, which was this beta, right, but it was the same thing. So this means that this Gaussian width, right, is smaller or equal than square root R, square root up to constants, plus square root n2. So this means that the number of measurements right? Needed is roughly, or up to constant, right? Roughly, that is, let me just say, right, so we're actually computing this, right, is roughly the square of this. So it's R times N1 plus N2. Right? So this is a lot less than the size of the matrix. The matrix would be N1 times N2. So say that N1 and N2 are the same. Let's say for the sake of right, for the sake of this example, let's say that N1 is equal to N2. Right? If N1 is equal to N2, then this, right, is simply like the rank times twice the length of the matrix, while the number of entries in the matrix would be N squared, right? Potentially much bigger. If R is small, this is a lot smaller. And in fact, you know, if you have a matrix, rank R matrix, then even if you knew, you know, even if you knew which were the R columns that were important, and when you looked at the other columns, you knew what linear combination they were of those R columns, you'd still have to measure those R columns, right? And those R columns would still take you R times N minus 1 measurements, okay? And this proof is also in the notes. All right, and here you don't, I mean, okay, so here we didn't have to union bound because we used this fairly strong, I mean, one way to prove this is to union bound. Right here, we use this result, and I used it without proving. But you could, for example, union bound over essentially like an epsilon net or something. You would get something of this type. And okay, but here we expect then that this, you know, matrix completion, matrix sensing at least can be done with only this many measurements. Okay, and this, right, and this indeed is the case, and it's, although it takes a bit more work to actually prove it, the more work that it takes is very similar to the one that it takes to make compressed sensing more rigorous, right? The S log n over S, and what we're going to see in the next lectures is we're going to derive all the things for compressed sensing and look at algorithms, and then with those ideas, one can also adapt this argument into rigorous things for matrix sensing and also matrix completion with a bit more work. All right, thank you.